Physics part 399. If a beam of electron is directed at a sample of powdered crystal and the electron wavelength is comparable with the interatomic spacing in the crystal, the electron waves are scattered from planes of atoms in the tiny crystals, creating a diffraction pattern. The fact that a diffraction pattern is obtained confirms the regular arrangement of the atoms in a crystalline solid. Measurements of the angles at which strong scattering is obtained can be used to calculate the distances between planes of atoms. If the energies of electron beam is increased, if the energy of the electron beam is increased, the wavelength decreases. Eventually, the electron wavelength may be of the same order of magnitude as the diameter of the nucleus. Probing the nucleus with high-energy electrons rather than alpha particles gives a further insight into the dimension of the nucleus and also gives information about the distribution of charge in the nucleus itself. We've got a section summary. The Rutherford alpha particle experiment confirmed that the nuclear model of the atom consists of small, heavy, positively charged nucleus surrounded by negatively charged electrons in orbit about the nucleus. The diameter of the nucleus is about 10 power raised to minus 15 meter. The diameter of the atom is 10 power raised to minus 10 meters. Electron diffraction gives evidence for the regular arrangement of atoms in crystals and allows the measurement of the distance between planes of atoms and solids. We've got exam style questions for the section. Cobalt-60 is often used as radioactive source in medical physics. It has a half-life of 5.25 years. Calculate how long after a new sample is delivered the activity will have decreased to 1/8 of its value when delivered. Question number 2. Iodine 131 is a beta emitter with half-life of 194 hours. It decays to xenon Xe. The decay is represented. A. Obtain the values of P and Q in the decay equation. B. A sample of iodine 131 of mass 0.20 gram is prepared in a reactor. Given that 0.13 kilogram of iodine 131 contains 6.02 into 10 power raised to 23 atoms, calculate the number of iodine 131 atoms contained in the sample at the time of preparation. Calculate the mass of iodine 131 which will have decayed 48 hours after preparation. Question number 3. The half-life of radioactive isotopes of sodium used in medicine is 15 hours. A. Determine the decay constant for this nuclide. B. A small volume of a solution containing this nuclide has an activity of 1.2 into 10 power raised to 4 disintegration per minute when it is injected into the bloodstream of a patient. After 30 hours, the activity of 1.0 centimeter cubic of blood taken from the patient is 0.50 disintegrations per minute. Estimate the volume of blood in the patient. Assume that the solution is uniformly diluted in the blood, that it is not taken up by the body tissues, that there is no loss by excretion. Question number 4. A fusion reaction that takes place in the sun is represented by the equation. A. Calculate the energy released in this reaction. B. Suggest why it is difficult to achieve controlled reaction of this type. Question number 5. A stationary radium nucleus 22488 Ra of mass 224 U spontaneously emits an alpha particle. The alpha particle is emitted with an energy of 9.2 into 10 raised to minus 13 joules, and the reaction gives rise to a nucleus of radon, Rn. A. Write down a nuclear equation to represent alpha decay of the radium nucleus. B. Show that the speed with which an alpha particle is ejected from the radium nucleus. The radium nucleus is 1.7 into 10 raised to 7 meters per second. Calculate the speed of the radon nucleus on emission of the alpha particle. Explain how the principle of conservation of momentum is applied in your calculation.